Hello, calculus friends. Here we will look at, I think it's about 5 problems from section 3.4 homework. These are the more challenging problems. Some of them are fairly rigorous respect to algebra. We're looking at the product rule, the quotient rule, and of course embedded chain rules. So let's take a look at problem 23, and perhaps what we can do is actually structure this in such a way that maybe it will be easy for you, okay? Personally, I see a product rule here, and let's take a look at it. So it would be useful to see this as u equals x squared, and v is equal to perhaps x minus 2 to the 4th power. The derivative of u here, so u prime, is just 2x, so a baby derivative. The derivative of v, so v prime, appears to be a little bit more menacing, and it could be. So if you're approaching this with a certain degree of trepidation, that may actually serve you well in the long run. So we have 4 times x minus 2 to the 3rd power. We applied the general power rule, and then yes, you're investigating, do we have an internal derivative? So we're aware of the chain rule, but the derivative of x minus 2 with respect to x is 1. So that's really not necessary. And then, of course, being aware of the derivative with respect to x of u times v, where u and v are differentiable functions, is u prime v plus u v prime. Once we understand that, all we're doing is pulling from the menu on top, and we're just plugging things in. So we're looking for u prime v. Well, we discover that u prime is 2x, and of course v is x minus 2 to the 4th power. And then what we're looking for, let's see, plus u times v prime. So u is x to the 2nd, and v prime is going to be 4 times x minus 2 to the 3rd power. So at this point, you're done with the calculus, and I'm almost sure that most of us got to this point, but if you're checking your answer in the back of the book, they will have factored out common factors. What are we looking at? Well, we're probably finding a common factor of 2 between these two expressions. We're looking for a factor of x between these two, and perhaps finding a factor of x minus 2 quantity to the cubed. In other words, we're looking for these common factors, but we're also always factoring out the smallest power or the lowest power. So f prime of x is equal to, between 2 and 4, we find 2 as a factor. Between x and x to the 2nd, we find x as a common factor. And of course, the quantity of x minus 2 to the 4th and x minus 2 to the 3rd, the common factor is x minus 2 to the 3rd, the lower power. So what is it that we have left? Well, we have left an x minus 2 to the 1st power. And let's see, we factored out the x, but not the x squared. So we should have a 2 times x, and I think that's it. Okay, if you're saying I'm struggling, I understand where we obtain these common factors, but how did we end up with these expressions? The answer is simple. What we need to do is whatever we factored out, we go back to the original expression for f prime of x, and yes, we have factored out the 2x and the x minus 2 to the 3rd power, but originally we had 2x times x minus 2 to the 4th plus, let's see, 4x squared times x minus 2 to the 3rd. Just snuck that in there. And we're dividing each of these by that common factor, the 2x times x minus 2 to the 3rd power. And that leaves us, when you simplify that, That leaves you with the quantity of x minus 2 to the first power. Here, you're dividing by the same thing, 2x times x minus 2 to the third, and the 4 divided by 2 leaves you with 2. The x squared divided by x gives you x, and of course the x minus 2 cubed cancels out, and that's how we end up with the 2x factor there. So that was the, I guess, the work in the back dealing with the algebra, and so ultimately you probably find the following answer in multiple choice presentations. So combining the x with the 2x, we have, let's see, 3x minus 2, and I think that this is the end of our journey. Challenging problem in the sense that we just had to persevere, but if you apply structure such as what I did here, it might make it easy for you to connect with the formula here and then simply plugging in to get the correct answer in terms of what we need for calculus on free response problems. For multiple choice, we needed to go ahead and continue progressing, and we have the answer through some interesting algebra, okay? And hopefully what we have here on the side, you'll find beneficial in terms of helping you with that sort of algebra, okay? All right, let's move forward. And so at this point, the next problem, again, an algebraically challenging problem, you are better off to rewrite this as, let's see, the quantity of 1 minus x squared to the 1/2 power. And if you benefited from the, identification of u, well, then we'll do that here as well. Very simple. And then v would, of course, be simply 1 minus x squared to the 1/2. And of course, u is easy to deal with. V, you already recognize that we're going to use the power rule. And then there is an internal derivative here, something other than 1, when you take the derivative of 1 minus x squared with respect to x. So we will be applying the chain rule. So u prime is 1. V prime is equal to, let's see, 1/2 times 1 minus x squared to the negative 1/2, and the internal derivative is negative 2x. Okay, that does simplify, and we'll do it here where it's not too busy. So the 2's cancel out. We have, let's see, a negative x times the 1, let me fix that, 1 minus x squared, that raised to the negative 1/2 power. So at this point, I think we can go ahead and simply assemble them according to the product rule, which should give you a u prime times v. That's simply 1 times 1 minus x squared, all that raised to the 1/2 power. And then v prime u or uv prime, whatever you prefer. Remember, this is our v prime, this is our u. So when I multiply them, we get a minus x squared times the 1 minus x squared to the negative 1/2 power. So once we've assembled this, again, you're done with the derivative. This is correct. You're done with the calculus. But the lowest power of 1 minus x squared happens to be negative 1/2, because that's smaller than the power of 1/2. So we will factor out the 1 minus x squared, and so to the 1/2, negative 1/2. And so what do we get? We end up with, because when you divide here by 1 minus x squared to the negative 1/2 power, you end up with simply 1 minus x squared to the first power. And when you divide here by 1 minus x squared to the negative 1/2 power, then you end up with simply minus x squared. So at this point, what do we have? Y prime. Here we have a negative exponent, so we'll move that factor into the denominator. And so we have, let's see, 1 minus x squared minus x squared, all that over 1 minus x squared to the 1/2 power. And we're almost done. Of course, you can see that we can combine the x squareds. And at this point, we have, let's see, 1 minus x to the 1/2 power in the denominator. And that concludes our adventures in taking the derivative here. Again, I think that you'll find that the derivative is relatively easy to take. We have it at this stage. We did have some staging in identifying u and u prime, as well as that's u prime, as well as identifying v. That was probably the productive portion, where then you were able to go ahead and apply the chain rule. You had, space and time to think about that, and then of course to actually simplify to end up with the simplified version of v prime, to bring that into the problem, which then of course allowed you to do the algebra to simplify from the correct answer that we have at this level, and then of course to arrive at the potential answer that you'll see perhaps on a multiple choice assessment or the back of your book. Now, continuing this adventure in calculus, we have hopefully a much nicer problem. The trigonometric problems tend to be a little bit easier. We do need to understand that it's not the sine function that is being squared here, but the argument of the sine function. Okay, so this is strictly the chain rule. Okay, but we are looking at, okay, the internal function happens to be, let's just call this u. So I'm going to look at this as the y equals the sine of u, and of course we can take that derivative, and then we'll discover that we have the y prime is equal to the cosine of u times u prime. I'm going to put the u prime in front so we don't confuse that as being part of the argument for the cosine function. But the question is, if u is equal to pi x squared, then what is the derivative of this with respect to x? And hopefully you are going to say, well, we're raising the pi x to the second power. So when we take the derivative, we're applying the chain rule. And so we have the power rule, which gives you pi x to the first power. And now we take the derivative of the internal function, and that is going to give you pi. So this is your internal derivative, that is the u prime. So when we express everything in terms of x, well, what do we get here? The y prime, the u prime is replaced by this entire expression. Probably we can simplify it here as u prime equals, let's see, 2 pi squared x, and so we have 2 pi squared x, and then we have the cosine, and not of u, because remember, the problem was presented to us in terms of x, so we will go with pi x quantity squared. And this is the expression that we're looking for. There were some challenges, but I think it's a much quicker process than the algebraic problems. So we're going to tackle number 55 here. We can obviously we can use the quotient rule as it is, or some of you may take a look at it knowing that the cotangent of x is equal to the cosine of x over the sine of x. So some of you may actually rewrite this as the cosine of x over the sine squared x, and of course there's nothing wrong with that. Then not only will you be using the quotient rule, but you'll also be using the chain rule. So I'm using this setup here, and of course u is equal to the cosine of x, and v is the sine squared x. So u prime is negative sine x, and v prime, remember, the sine x is raised to the second power, so the sine function is squared. So the general power rule gives you 2 sine x, and then the internal derivative, which happens to be sine of x, gives you the derivative of cosine of x. And so let's go ahead and apply the quotient rule. And so the derivative of the cosine is negative sine x. That's multiplied by the denominator, which is sine squared x. And now we, of course, have, let's take a look at what do we have here. The derivative of the denominator, and that's going to be minus, let's take a look at u. So that's cosine of x, and then we have 2 times sine x cosine x. We'll pretty that up in a second. In the denominator, we have the sine to the 4th of x. We're squaring the denominator. And so let's see if we can make this look better. We have the negative sine cubed x, and then let's see minus sine, 2 sine x, and the cosine squared x. Okay, all that over sine to the 4th of x. Now this is f prime of x, and we're going to engage in further simplification. Let's see what we have. We have a common factor of the sine of x, and so we can factor that out, and we end up with, let's see, sine x, and we have the negative of the sine squared x minus 2 cosine squared x. Okay, all that over sine to the 4th of x. So we will end up with a canceling out, and what do we have? We have in the denominator a sine cubed of x. And in the numerator, of course, the sine x has canceled out, but we have to do a little bit of rearranging, okay? And let's see how we can make that happen. I believe that you see here that we can factor out a negative 1. And when we factor out the negative 1, that leaves us with a sine squared x. And then we have plus 2 cosine squared x, but we could separate that into plus cosine squared x and plus cosine squared x. And you might say, well, why are you doing this? The reason why is that we know from our pre-calculus days that this is another name for 1. So ultimately, the simplified version of our answer is that f prime of x is equal to, let's see, negative, and I'll keep that negative 1 out here. And so we have 1 plus cosine squared x, all that over sine cubed x. Now this is a correct answer. This is wonderful. Of course, there was another way to do this, which was to simply tackle this as the problem was presented, so that you would end up using, let's use a different color. So u would, of course, be equal to the cotangent of x, and then, of course, v would be the sine of x, and so u prime would be equal to the negative, let's see, cosecant squared x, and of course v prime is the cosine of x, and of course you could go ahead and assemble that. That will give you an equivalent answer logically, but it'll look a little different. And then of course, if you would want to go ahead and rewrite it in the format that I have here, then you would need to do some additional massaging algebraically and using trigonometric identities. I will let you experiment with that and see if you could successfully navigate to this form of the correct answer. Okay, moving on. Let's take a look at it. Number 59, a relatively manageable problem, but let's rewrite it as the tangent of 5 theta, all that being raised to the second power. So at this point, we have basically an internal function of 5 theta, and of course, a little bit further out, we have tangent of that 5 theta, and then of course, we have this square function here, okay? So we could certainly set this up. You don't need to, but we could end up setting this up as perhaps u is equal to the tangent of, let v equal 5 theta, okay? And let u equal the tangent of v, okay? And so then, of course, we have the outer function. Let me create a little bit more room here, if you don't mind. So we have u is equal to the tangent of v. And then meanwhile, we have f of u, which is equal to u squared. Okay, so we can certainly solve this problem as it's set up at this point in time. And some folks actually set this up as y is equal to u squared. And so then dy du is equal to 2u, okay? And then meanwhile, you end up with du dv is equal to the secant squared v, and dv d theta is equal to 5. And if you look carefully, okay, and if you're looking for dy d theta, then if you set this up as dy du, where's that coming from? Right here, times du dv, and then of course we have the dv, that's a v, dv d theta, we end up with proper substitutions with the correct answer, but let's take a look at this. So the du's cancel, and the dv's cancel, and that leaves you with indeed dy d theta. So this is a nice setup, and of course we will start importing right here. This is the equivalent of 2u, and then of course the secant squared v, and times 5. Now, ultimately, you'll want to replace the u's and v's with the appropriate variables in terms of theta. So dy d theta ends up being equal to, let's see, a 10, the 2 times 5. U is equal to, let's take a look at, here we go, the tangent. But remember, we don't want the tangent of v there. V is equivalent to 5 theta, so that's the argument. That was the way the original function was presented. And then, of course, we end up with, let's see, the secant. So far, let's make sure we know what we're doing. We have dy dv, okay? And then, of course, we have du dv, which is going to be the secant squared v. And again, there's no v there, it's 5 theta. And so once you have that, I think we are at the end of our journey. We had made all the appropriate substitutions, okay? Now, if you're saying, that was a lot, well, let's see how we could make it a little bit easier. If you take a look up here, we have 3 functions, 1, 2, 3. They're sort of nested. And if you take the derivative of the outer function, so let me go ahead and just give myself a little space here. We have f of theta is equal to, the derivative of the outer function is 2 times the tangent of 5 theta. Then the derivative of the tangent, okay, is going to be secant squared, and don't change the argument in there, 5 theta. And then the derivative of the function inside there, the argument of the tangent, is 5. And so at this point, if you, that's f prime. So if you take a look at this, 2 times 5, so that's 10. Tangent of 5 theta times the secant squared 5 theta. If we compare what we have here, I think we'll discover that this is indeed a favorable comparison. So sometimes, again, there are some tools with which to simplify the problem, or better yet, I don't think that was simplification, to structure the problem if you need that. However, I believe that the second technique is going to be the easier route for most of us. Okay, so let's continue our work. And we're going to do a wrap here with number 63. Let's take a look at what we have here. Uh-oh, let me move this back. And so we have, I think, a nice way to write this is 3 times the secant of pi t minus 1, and all of that is raised to the second power. So this is a little bit easier to see in the sense that we are going to have some nested functions here. We have the internal derivative would be for, well, the argument of the secant is pi t minus 1. Then we have the secant raised to the second power. So ultimately, we're looking at something like 3u squared. And of course, u is defined as secant of pi t minus 1. So let's begin by taking the derivative of the outer function. The 3 is there as a constant multiple. It's not going to impact our derivative, but we have f prime of t. And then we have 3, that constant multiple. The general power rule brings the exponent of 2 down. And then, of course, we have the secant of pi t minus 1, okay, raised to the first power. But now we're taking the derivative of the secant, which, of course, gives you the secant of pi t minus 1 times the tangent of pi t minus 1, and then the internal derivative. So we're still left with the derivative of pi t minus 1, and of course that derivative is pi. Okay, so taking the derivative of the argument, the internal expression, we end up with pi, and so setting this up in a nicer, more concise fashion, but the calculus is done. What do we end up with? I believe a 6 pi would be appropriate, 2 times 3 and then the factor of pi in the front. We do have a secant of pi t minus 1. We have 2 of those factors, so squared. And then, of course, we have the tangent of pi t minus 1. And this brings us to the end of our journey in this quest. And until next time.